Welcome to the deep dive. The world of artificial intelligence can feel like you're constantly encountering new vocabulary, a whole new language evolving at, well, breakneck speed.
It really can. Seems like every week there's a new term.
Exactly. So today we're going to try and cut through some of that complexity and get to the core of what some key AI terms actually mean.
Yeah, terms like AGI, deep learning, even things like hallucination, they're everywhere now. Our goal in this deep dive is really to give you a clearer picture, moving past the buzzwords to what they actually signify.
And we've got a great resource for this. It's a glossary of important AI terms from TechCrunch, just published yesterday, May 25th, 2025. And they actually keep it updated regularly.
Which tells you something right there, doesn't it? How fast things are moving. You almost need a constantly updated dictionary just to keep up.
Totally.
Yeah.
So our mission today is pretty straightforward. Help equip you with a solid understanding of these fundamentals. Let's dive right in, shall we? Maybe start with one that gets a lot of attention but also seems, well, a bit vague sometimes. AGI.
Artificial general intelligence. Yes, definitely captures the imagination. And the glossary rightly calls it a nebulous term. What's really interesting, I think, is how even the big players define it slightly differently.
Right. They mention OpenAI's CEO, Sam Altman. His definition is something like the equivalent of a median human that you could hire as a coworker.
Which paints a picture, doesn't it? A sort of generally competent AI coworker.
Yeah, capable across the board. But then OpenAI's own charter has a different spin. Highly autonomous systems that outperform humans at most economically valuable work.
See, that's a subtle shift, isn't it? It brings in outperform humans and focuses on economically valuable work. It's not just about being like a human, but better in ways that, well, matter for business and the economy.
That's a really key distinction. Are we trying to just replicate general human ability or specifically exceed it where it counts economically?
Exactly. And that difference could really shape where research goes, what we expect from AI down the line.
Then you've got Google DeepMind defining it as AI that's at least as capable as humans at most cognitive tasks. So focusing more on the thinking, the cognitive side.
Right. So you have these slightly different angles even from the leading labs. It just underlines that we're still figuring out what AGI truly means, or even if it's achievable. There's no single agreed-upon definition yet.
Okay, so AGI is the big, maybe distant, potentially human level or beyond goal. Let's move to something maybe a bit closer to reality now, AI agents.
Yes, AI agents. These sound like they could become much more practical and integrated into our daily lives, maybe sooner rather than later.
The glossary defines them as tools using AI to perform a series of tasks for you. So going beyond just a simple chatbot conversation.
That's the key bit, I think, this series of tasks. It's about autonomy in action. Examples they give are things like filing your expenses, booking tickets, or maybe restaurant reservations, even writing or maintaining code.
So it's not just answering a question, it's actually doing stuff for you, multi-step stuff.
Exactly. It's like an assistant that can understand a goal and then figure out the steps needed to achieve it, potentially using different AI tools along the way.
Interesting. The glossary does mention, though, that the field is still developing and the exact meaning can vary.
Yeah, it's still quite fluid. But the core idea seems to be an autonomous system that pulls together different AI capabilities, maybe language understanding from an LLM, planning abilities, using specific tools to get a job done that involves multiple steps.
Okay, so AI that can plan and execute. Got it. Now, another term that pops up a lot when talking about how these AIs, especially language models, work is chain of thought.
Chain of thought reasoning, yes. It's a really interesting concept. The TechCrunch piece uses a good analogy. You know that old riddle about chickens and cows in a field where you know the total heads and legs?
Right, you can't just guess the answer. You have to work it out. Like, okay, chickens have 2 legs, cows have 4. You do the math step by step.
Precisely. You need those intermediate steps, and that's basically what chain of thought reasoning is for AI. It's getting the AI to break down a complex problem into smaller logical steps, almost like showing its work.
And doing that helps it get the final answer right more often.
Yes, especially for problems involving logic, math, or coding. It forces a more structured approach, which generally leads to more accurate results, even if it takes the AI a little longer to generate the response.
So accuracy over speed sometimes makes sense for complex tasks.
Exactly. And often, these reasoning models are developed from standard large language models, but then they get specific training using reinforcement learning to get better at producing those step-by-step thought processes.
Reinforcement learning. Another term for the list.
Yeah.
But sticking to the basics, let's talk deep learning. This seems to be the powerhouse behind a lot of recent AI progress.
It really is. Deep learning is a specific type of machine learning. The key thing is that it uses artificial neural networks with many, many layers. That's the deep part.
And having lots of layers lets it find more complicated patterns.
That's the idea. This structure allows it to learn really complex correlations in huge amounts of data, much more complex than simpler machine learning methods could handle. The whole structure is famously inspired by how neurons are connected in the human brain.
Right, the neural network connection.
And what's powerful is that deep learning models can often figure out for themselves which features in the data are important. You don't necessarily have to tell them exactly what to look for.
That's a big shift from traditional programming, isn't it? They learn what matters.
They do, and they learn from mistakes. They process data, make predictions, see how far off they were, and adjust themselves to do better next time. It's an iterative learning process.
But it needs a lot of fuel, right? The glossary mentions huge data sets.
Oh, absolutely. That's the catch. Deep learning typically requires massive amounts of data, millions of examples, sometimes more. And training these big models takes a lot of computing power and time, which translates to higher development costs.
Got it. Big data, big compute, big potential. Now, shifting to something generating buzz in the creative space, diffusion. This is behind a lot of the AI art and music generators, yeah.
Yes, diffusion models are fundamental to many of those tools. The glossary uses a nice analogy from physics. Think about taking structured data, like a clear image, and gradually adding noise like static until the original structure is completely gone.
Okay, so you basically destroy the information methodically.
Right. Now, in physics, like sugar dissolving in coffee, that process is usually one way. You can't easily undissolve the sugar. But the trick with AI diffusion models is they learn to reverse that process.
Ah, so they learn how to take the noise and reconstruct the original image or data.
Exactly. They learn to denoise step by step, effectively going from random noise back to a coherent image or piece of music or even text. That's how they can generate new, original-seeming content from basically nothing.
Wow, okay. Reversing entropy, almost. Very cool. Now, how about distillation? Sounds like we're boiling something down.
In a way, yes. AI distillation is about transferring knowledge from a very large, complex AI model, the teacher, to a smaller, more efficient model, the student.
Why would you do that?
To create a smaller, faster model that performs almost as well as the big one, but uses fewer resources. Think about putting powerful AI onto a smartphone or making a web service respond faster.
Okay, so efficiency. How does the knowledge transfer actually work?
Typically, you feed lots of requests to the big teacher model and record its outputs, its answers. Then you use those outputs, essentially the teacher's examples, to train the smaller student model to mimic the teacher's behavior.
So the student learns by copying the teacher's answers.
Pretty much. It learns to replicate the patterns and decisions of the larger model. The glossary suggests this might be how models like GPT-4 Turbo became faster, possibly distilled from a larger version.
Interesting. And they also mentioned this can be used internally, but also raises questions if companies try to distill competitors' models.
Right. That's an ethical and legal gray area. If a company uses distillation to essentially copy the capabilities of a competitor's model by feeding it prompts and training their own model on the outputs, that could violate terms of service.
Okay. Good to know. Let's move to fine-tuning. This sounds more straightforward, making an existing model better at something specific.
That's exactly it. Fine-tuning means taking a pre-trained model, often a big general one like an LLM, and training it further on a smaller, more specific data set to make it really good at a particular task or understand a specific domain.
So, like taking a general language AI and feeding it loads of medical journals to make it an expert medical Q&A bot.
Perfect example. A lot of AI startups do this. They take a powerful foundation model as a base, then fine-tune it with their own specialized data, maybe legal data, financial data, whatever their niche is, to make it much more useful for their target customers.
It's like giving a generalist some specialized expert training. Makes sense. Okay, here's one with a cool name. GN, Generative Adversarial Network. What's the adversarial part about?
GNNs are really clever. They're a machine learning setup that's been key for generating realistic outputs like photorealistic faces or deepfakes. The core idea involves two neural networks competing against each other.
Competing? Okay, how?
You have a generator network and a discriminator network. The generator tries to create fake data, say, a fake image that looks totally real. The discriminator's job is to look at both real images and the generator's fake images and try to tell which is which.
Ah, so it's a constant battle. The generator tries to fool the discriminator, and the discriminator tries to catch the fakes.
Exactly. It's an adversarial game. And through this competition, both networks get better. The generator gets better at making realistic fakes, and the discriminator gets better at spotting them. This pushes the generator to produce incredibly realistic results without needing constant human feedback.
Clever. But the glossary says they may be better for narrower tasks.
Yeah, they tend to excel at specific generation tasks, like creating realistic photos within a certain category rather than being suited for, say, general-purpose language understanding.
Got it. Okay. Now, for a term that sounds a bit worrying, hallucination. This doesn't mean the AI is literally tripping, right?
No, no. In AI jargon, hallucination means the model generates information that's just plain wrong or nonsensical or completely made up, but it often states it very confidently.
Ah, so it's like confidently incorrect.
Exactly. And the glossary rightly points out this is a major problem for AI quality and trustworthiness. Imagine getting confidently wrong medical advice or legal information. It can be misleading or even dangerous.
Yeah, that's why you see those disclaimers everywhere, like always check the AI's answers.
Precisely. The leading theory about why this happens is usually gaps or maybe inconsistencies in the massive data sets these models are trained on, especially for the huge foundation models trained on like half the internet. It's almost impossible to ensure all that data is accurate and complete.
So it learns some bad facts or fills in gaps incorrectly?
That seems to be the thinking. And this problem is actually driving a trend towards more specialized AI models. If you train an AI on a narrower, more curated data set, say, only verified scientific papers, you reduce the chances of it learning and repeating misinformation.
Makes sense. Limit the knowledge scope to improve accuracy. Okay, so after all the training, we get to inference. What's that?
Inference is simply the process of using a trained AI model. You feed it new data it hasn't seen before, and it makes a prediction or generates an output based on what it learned during training.
So training is the learning phase, inference is the doing phase. Like you train a cat detecting AI.
Yeah.
Then inference is when you show it a new photo and it says cat.
Perfect analogy, yes. Inference is putting the trained model to work, and obviously it relies completely on good training beforehand. It can happen on all sorts of devices too, your phone, powerful servers with GPUs, specialized AI chip.
And bigger models probably need more power for inference, right?
Generally, yes. The complexity of the model and the hardware available determine how fast and efficient inference is.
Okay. Now, we've mentioned them a lot. Large language models, LLMs. Let's define those properly. They're behind things like ChatGPT, right?
Absolutely. LLMs are the engines powering most of the popular AI assistants you hear about. ChatGPT, Claude, Gemini, Llama, and so on. When you chat with one of those, you're talking to an LLM, essentially.
And it's good to remember the distinction. Like GPT is the model, ChatGPT is the product using it.
Exactly. Technically, LLMs are a type of deep neural network, but they are characterized by having a truly enormous number of parameters, sometimes called weights. Billions, even trillions sometimes.
Billions of parameters. Okay, we'll get to weights in a sec, but what do all those parameters let the LM do?
They allow the model to learn incredibly complex patterns and relationships between words and concepts in language. You can think of it like the model building a vast multidimensional map of how words relate to each other.
A map of language. I like that. How does it build this map?
Through training on unimaginable amounts of text data books, articles, websites, code, transcripts, everything, it learns the statistical likelihood of words appearing in sequence. So when you give it a prompt, it generates a response by predicting the most probable next word, then the next, and so on, based on the context and its internal language map.
So it's like a super sophisticated prediction machine for language.
At its core, yes. Extraordinarily sophisticated pattern matching and prediction.
Okay. And underpinning LLMs and deep learning is the neural network. We touched on this, but let's circle back.
Right. The neural network is that multi-layered structure of algorithms. The basic idea, inspired by the brain, actually goes way back to the 1940s.
So why the big explosion now?
A huge factor, as the glossary highlights, was the rise of powerful GPUs, graphical processing units, driven initially by the video game industry needing better graphics.
Gaming GPUs helped AI. Seriously.
Yeah. Absolutely. It turned out those GPUs were fantastic at the kind of parallel calculations needed to train really deep neural networks with many, many layers, Suddenly, researchers could train much bigger, more complex models than before. That computational power unlocked the potential we're seeing now across so many fields: voice recognition, self-driving cars, drug discovery.
Amazing.
Yeah.
A completely unintended consequence of better video games.
Yeah.
Okay, let's define training itself more formally.
Sure. AI training is the whole process of feeding data into a model so it can learn patterns and relationships and eventually produce useful outputs. Before training, the model is just a structure, maybe with random numbers in it.
Like an empty brain, sort of.
Kind of. Training is how it learns. It processes the data, adjusts its internal settings, those weights we'll talk about, to get better at achieving whatever goal it's designed for, like classifying images correctly or predicting the next word.
And it needs data to learn from.
Usually, yes. Although, it's worth noting, not all AI needs training like this. Old school, rules-based AI just follows instructions. But for the learning AI we're mostly talking about today, training on data is key, and it can be very expensive because of the data and compute needed.
Right. Which leads nicely into transfer learning. Is that a way to make training more efficient?
It is. Transfer learning is basically taking a model that's already been trained on a lot of data for one task and using that pre-trained model as a starting point to train a new model for a different but related task.
You don't start from zero. You leverage the previous learning.
Exactly. You transfer the learned knowledge, the patterns it already discovered. It can save a lot of time and data, especially if you don't have much data for your new specific task. You're building on an existing foundation.
But it might still need some tweaking for the new task.
Often, yes.
No.
You might still need to do some fine-tuning on the new task's data to get the best performance, but it's usually much faster than training from scratch.
Okay, transfer learning is like getting a head start. Finally, let's tackle weights. LLMs have billions of them. What are they?
Weights are absolutely crucial. They are numerical values inside the neural network that determine how much importance or influence is given to different inputs or connections within the model. Think of them as dials that control the signal strength between different points in the network.
So they decide what the model pays attention to.
In essence, yes. They define what's important in the data for the task at hand. During training, the model starts with random weights, and then, as it learns, it adjusts these weights up or down to make its outputs closer to the correct answers in the training data.
Can you give an example?
Sure. Imagine an AI trying to predict house prices. It looks at features like square footage, number of bedrooms, location. The weights assigned to each feature would reflect how much that feature influences the price based on what the model learned from all the house price data it was trained on. A good location might get a high weight, while maybe the color of the front door gets a very low weight.
Ah, okay. So the weights are the learned knowledge, encoded as numbers that control the flow of information.
That's a great way to put it. Those billions of weights in an LLM represent its incredibly complex understanding of language, learned through training.
Wow. Okay, well, this has been incredibly helpful, really breaking down some of that dense AI vocabulary. We've gone from AGI all the way down to the fundamental weights.
And hopefully it gives you a much better foundation for understanding AI news and developments. As that TechCrunch glossary shows, knowing the language is key, especially as this tech becomes more embedded in everything.
Absolutely. And remembering it's always evolving, hence the need for updated glossaries. But hopefully this deep dive gives you, our listeners, a solid framework.
So maybe something to think about is, which of these concepts, diffusion, agents, maybe fine-tuning, do you think will most impact your world, your job, your industry in the next few years? What other questions does this bring up for you?